Welcome to the fifth lecture in the series of lectures on Galilean Laws of Motion by DHS Maithripala. And in this lecture, I will be concentrating on describing the motion of a rigid body. In a previous lecture, we saw how to describe the motion of a collection of particles, a set of particles. So we have a set of particles that we are interested in. These particles are interacting with each other as well as the particles in the universe, the rest of the particles in the universe. So if I denote by FIE, the interaction that the ith particle in our system feels due to its interaction with the rest of the particles in the universe. And if I represent that position of that particle by xi in terms of a reference frame, we get that the total momentum acting on the particle is given by this, and the total external forces resultant of the external forces acting on the set of interacting particles is given by this, the summation of all the forces acting on the particles. And so this is by definition then the force moment acting on the particle about point O, and then this is the angular momentum of the particle acting on the acting about the point O of the frame, the origin of the frame. And so this is the total momentum, this is the total moment of the force, this is the total force, external force, and this is the total linear momentum. So we saw that when you differentiate this, we get that the total momentum is equal to the total resultant of the external interactions acting on the particles, or the external forces acting on the particles. Then from this, we also saw that by substituting this, using this expression over here, the total mass of the set of particles, if it is capital M times the acceleration of the center of mass is also equal to the external forces, resultant of the external forces acting on the particle. So we saw that also. Then we also saw that the rate of change of total angular momentum is given by this, and if the frame is located at the center of mass of the set of particles, then the rate of change of angular momentum is actually equal to the total resultant of the force moment of the external forces acting on the particle. So we saw this in a previous slide. And also we saw that the configuration of a rigid body. So what is a rigid body? A rigid body is a set of particles where the relative distance between any two particles remains fixed. So if you have such a body, then you can fix a frame onto the body, frame B, and you will have an earth fixed frame E. Then the configuration of the rigid body is uniquely given by the relationship between the frame fixed to the body and the inertial frame E. So we saw that that can be given by this expression of the location of the origin of the body fixed frame with respect to the E frame, simple law, and the relationship between the B frame and the E frame given by a special orthogonal matrix. So the pair O and R, where O is a element of R3, order triple number, and R is an element of the special orthogonal matrices, uniquely determines the configuration of a rigid body. So we also saw that this pair can also be written as a 4x4 matrix, and that set of all possible such 4x4 matrices are called the Euclidean motion group. And if you just write down the kinematics, so what do you mean by the kinematics? The velocities of the part of a rigid body. Then since the rigid body is uniquely described by O and R, the derivative of those uniquely determine the velocities of all the particles with respect to the E frame. So that can be used as a representation of the velocities of the rigid body with respect to the E frame. So if you write it down, well, when you differentiate this, you get that. For R dot, you replace this. For O dot, if you define R transpose O dots, remember the coordinate transformation interpretation. So what this means is O dot as viewed in the B frame. So what is O dot? When you write it down as components along B1, B2, and B3 is capital B. So if you plug all of that over here, this and that, you get that. And this can also be written down as something like G dot is equal to G psi, where this is G theta, where that is. So let's, so in the previous slide, when I considered the set of particles, those were any collection of particles interacting with themselves as well as the rest of the particles in the universe. So let's try to specialize these expressions to the case when the relative distance between any two particles remains fixed. So we saw this, these were derived before. And then the center of mass, if you write it down in terms of the body frame quantities, you can write it this way. Then the velocity of the center of mass, when by differentiating this, you get that. Now, since the center of mass is always appearing to be fixed with respect to the body frame or the frame fixed in the body, this term will be 0. And then if you write down similarly, because of that, if you differentiate this again, you get the acceleration of the center of mass of the rigid body with respect to the inertial frame. The simple quantities denote that are related to the body frame quantities by this expression over here. Now, if you plug this expression over here into this one, so what do we get? We get this. So this is nothing but a restatement of this expression using body frame coordinate. Why? Because the center of mass can be written down in this form. Then the center velocity of it can be written down like that. The acceleration can be written down like that. Now, if you plug it all over there, you get this equation is equivalent to this. So what have we done here? We have simply written down the fact that the rate of change of linear momentum of all the set of particles is equal to the external forces acting on the particle. So now that is this. Now this is expressed in quantities that are in the E frame or the inertial frame. So P is a quantity that is expressed in the inertial frame. The total resultant force is expressed in the E frame. Now all we have done is using these expressions, converted that into expression that is completely written down in terms of the body frame variables, body angular velocity, and so on. Well, this is actually in the Earth free frame, but if you take R transpose O double dot, that is a quantity again in the frame fixed in the body. Similarly, if you write down this expression, if you plug it in this one, and if you write down that expression in the body frame, you will get this. And so if you, okay, so let's go to the next one. So again, so if you write down so in this frame, we will try to write down what this body angular momentum, sorry, the angular momentum of any given particle expressed in the E frame. And let's write it down in the B frame quantities. We saw that can be written down this way. So if you add all of these together, you get the total angular momentum of the particles of the rigid body, and they can be expressed in the E frame quantities. And this quantity appearing over here, if you look at it, it is a property of the point. And if you add all of these together, you get what we call the moment of inertia. So in this expression gives you the moment of inertia of the point P about point O prime. If you add all of them together, you get the moment of inertia of all the particles about the point O prime. That's that point. So using this expression, we can write it this way. Then this quantity over here has the interpretation that it is the same as this, but represented in the body frame coordinates. So that is the spatial angular momentum expressed in terms of how much along B1, how much along B2, and how much along B3. That's that. So we saw this also in a previous slide. So let's differentiate this. So here in these equations, I'm just summarizing what we have seen so far. Now, if you differentiate both these sides, you get this expression over here. Now, if you use the Jacobi property of cross products, which is this one, you end up by rearranging these terms. You can rearrange these terms, and you end up with this expression over here. So you end up with that expression over here. And And also recall that we had showed that the rate of change of angular momentum as expressed in the E frame can also be written down in this way. So we have two expressions derived for the rate of change of angular momentum. By equating the two, what do we get? So we have two of them. By equating the two, we get the following expression. So this expression nicely describes the collective behavior of a set of particles totally in terms of the body frame quantities, the quantities that are expressed in terms of the B frame, or the frame that is fixed to the body. Omega is the angular momentum, I is the sum of all the moment of inertia about the point O, which is given by that. And then this term is the acceleration of the origin of the frame, but expressed in the B frame, because R transpose O dot is that. So R transpose tau is what? The total resultant moment of the forces about this point expressed in the E frame. But when you multiply by R transpose, what that means is the same quantity expressed in the B frame. How much along B1, how much along B2, and how much along B3. So what we have done is we have expressed the rate of change of angular momentum of all the particles in terms of body variables in the body frame, in two different ways. We have done it in two different ways, compared them, and obtain a relationship that has only body frame quantity. And similarly, you can do this for this expression as well. So what we have done is converted those, not really converted, so that the equations that we derived for a set of interacting particles, under the restriction that the particles, the relative distance between any two particles remain fixed, gives you that those expressions that govern the rate of change of angular momentum and rate of change of linear momentum result in these two expressions, which are completely expressed in terms of quantities that are with respect to the frame fixed to the body. So that's again a restatement of these two. So now if you take the cross product of this with the center of mass with respect to the body frame, expression of the center of mass with respect to the body frame, I'm just getting the cross product of this equation with that. I get this over here. Then use this property, which we derived some time ago, to obtain these properties. You can, I will give you assignment. There's an assignment in the lecture note that invites you to show these properties. We can just plug this thing. So you take the cross product of that is that, and you plug it in over here. And what do we get? We get this expression over here. And if you define this quantity, so if you notice that it is also like a moment of inertia term. So if you define that quantity to be Ix, and then this whole thing can be written down like this expression over here. And so what do we get? We get this expression once you substitute for this by taking the cross product with x bar of that expression becomes this, where IC is now I minus Ix. So if you just go through these calculations, you will notice that this whole thing combining this with that gives you this. You define Ix to be this, then this whole thing, complicated thing, can be written down in terms of, in a very compact way using that over here. And this is actually called the parallel axis theorem. Now, if you fix up until now, we had just arbitrarily fixed the frame in the body, set of particles, the rigid body. But there's no reason why we should not place it at the center of mass, so that we can simplify those equations. So if you fix the frame that is fixed to the body at the center of mass of the set of particles, then x bar is 0, and those equations simplify into a very nice compact form, and these are called the Euler's rigid body equations. The last equation, this one over here, can also be conveniently written down in terms of the E frame quantity. So sometimes it is convenient to use this and this expression over here, or the equivalent expression, that is that expression over here. So if you write down, so that was in terms of angular velocities. So if you write down in terms of the angular momentum, so the total rate of the total angular momentum of the set of particles is given by this. Now this quantity over here is the body frame representation of that, because that is this interpretation, coordinate transformation interpretation. Now if the body frame is fixed at the center of mass, this term becomes 0, and we have a very compact representation of the body frame version of the total angular momentum of the set of rigid body of particles that comprise the rigid body. So this term, then this becomes simply that. That's called the body frame version of the angular momentum, or for short, body angular momentum. Now, if you write down this Euler's equation in terms of the body frame quantities, you get this equivalent set of equations. So we derive this by fixing the frame at the center of mass. This just converts to this, and so sometimes it is convenient to use these equations, sometimes it is convenient to use these equations. And also we saw that, well, the spatial angular momentum version, that is this, well, this is the one that we derived at the beginning itself, irrespective of whether it is a set of rigid bodies, can be written down in the following form, in this form. And if you notice, we can define, so since we saw that omega is the angular velocity of the frame B with respect to the frame E, and represented in the frame B coordinates, and if you multiply that, the coordinate transformation interpretation tells you that this is this, but expressed in the E frame. So the angular velocity, if you write it down in terms of how much along E1, how much along E2, and how much along E3, you get simple omega, and that we call the spatial angular momentum. Now, if you write this down, so then we get an equivalent version of the body angular momentum in terms of, the spatial angular momentum in terms of the spatial angular velocity. And this is called the spatial inertia tensor, or the locked inertia tensor. And I just, so we saw how to write down Euler's rigid body equations using body angular velocities, body angular momentums, and now in terms of spatial angular velocities and spatial angular momentum. So let me summarize all of these three things. So we have written down that the motion of a set of particles that are interacting with each other, as well as the rest of the universe, in such a way that the relative distance between any two particles remains fixed, can be described very conveniently by a very few equations. So you can have a million, billion particles, but all the effects of that particles can be represented very conveniently using this O and the R that relates this to that, the B frame to that, and these expressions over here. So this is in terms of completely spatial velocities and spatial momenta. This is in terms of body velocities and body momenta, and this is in terms of body momenta. In this one, this is body angular velocity. So if you look at this expression, this is the total force, the moment of inertia of all the particles about the origin of the frame fixed to the body. And one can easily show that this is symmetric and positive definite. You can easily verify that this is symmetric and positive definite. And what that means is it can be diagonalized. Since it is symmetric and positive definite, it can be diagonalized with real diagonal elements, and they are the eigenvalues of this inertia tensor. Now, if you align your frame, body frame, so that they align along the principal axis directions, or the eigenvectors of this matrix, then you get a very simple form. So I is a diagonal matrix. You write down Euler's equations using the diagonal matrix. They reduce to these three equations over here. And then the spatial, the body angular momentum version also reduces to this. So Euler's rigid body equations, if you fix a frame at the center of mass and align the axes along the principal axis of moment, or in other words, eigenvectors of the inertia tensor, then you get this expression reduced into these three equations, this matrix expression reduced into this expression over here. So I will conclude this lecture by deriving the kinetic energy of a rigid body. So kinetic energy is nothing but the kinetic energy of the total kinetic energy of all the particles in the set of rigid body in the body. Now this is expressed in terms of the inertial frame always, and in terms of the inertial frame, it is 1/2 the mass times the velocity, magnitude of the velocity squared. You add all of those together, you get the total kinetic energy. Now let's write that down in terms of the body quantities. So you write this down in that using the body quantities, and then you just compute that. And what we find is that the kinetic energy can be written down in a very compact form using this. And then the rate of change of kinetic energy is given by this expression over here. And these expressions will turn out to be very useful when we are analyzing the motion of rigid body.